Hello everyone and welcome back to my computer vision channel. Today we will be talking about MOTR, the multiple object tracking model based on transformers. It is quite similar to TrackFormer but a bit different, so today we'll go over similarities and differences as well. And here's the plan for today. So we'll start with the overview of the method. So what is DETR? How can we modify that to do tracking? And what sort of loss is used? Then we'll go over the training datasets and the first difference of MOTR to TrackFormer, that is the actual number of frames that we pass into the model itself. Then we'll talk about the time aggregation network. So this is an extra layer that is responsible for carrying over the queries from frame to frame. Then we'll just basically go over all the differences of MOTR to TrackFormer once again. And then we'll talk about results. And so I'm mainly going to compare this model to TrackFormer because it's so similar and the actual approach is really quite the same, but there are slight differences. And to actually understand what those differences mean, we'll also need to understand what sort of metrics can be used. And this is a quite complicated topic because honestly, a lot of resources on the internet are not really well written to understand what these metrics are. So I'm going to quickly go over all of them, describe what is the difference and what is the difference of MOTR and TrackFormer as reported by these metrics. And then we'll go over the actual results of the model. And let's start with the overall method overview. So first, let's talk about DETR, which is the first and probably most famous model for object detection with transformers, and everything else in the field is sort of built up on top of that. So here's how it looks like. So we start with an image that might look something like this. So that image is fed through what we call a backbone, which is an image detection model that can be something like ResNet based on convolutions or swing transformer based on transformers as well. For our purpose, we don't really care. What we do care about is that we get some processed version of the image, which is usually of much smaller resolution. But then each pixel in this processed image now has features about everything that's going on there. So instead of looking at raw pixels, we're going to look at high-level features like heads and shapes and colors and objects and so on. So then that image is basically flattened and fed into transformer. Transformer itself, as well as this flatten operation, sort of loses the initial positional information of every pixel that we had. So to compensate for that, we also have positional encoding, which is just added to features of every pixel. That is fed through transformer encoder. So both transformer encoder and decoder, basically input and output shapes are going to be the same. So this whole operation that is going to perform this full pairwise self-attention between each pair of pixels basically creates a more processed version of the image, where now every element in the image was allowed to attend to every other element in the image in every layer. So now our understanding of what is going on within the picture is much better. Then this processed version of the image is used in transformer decoder. So decoder can be seen as something that now operates on a different shape. And in our case, we are interested in the actual detections. And so input to that, which we call object queries, are basically experts that try to query the image for some objects. And so the output, which is the same shape, are basically embeddings, which are then projected into the actual class predictions and bounding box predictions. So bounding box is just 4 numbers that allow us to say where the object is. So object queries, in case of DETR, are just static parameters, meaning that they do not depend on the actual image, but they are trainable. So during training, DETR actually learns to have some useful queries that serve somewhat as anchors to do good detections on the image. So now, important part of this, which we will go over again and again in the current video, is the Hungarian matching loss. So Hungarian matching loss allows us to actually compute loss for the model. And so the problem we're trying to solve here is called direct set prediction. So we might have a different number of objects in the picture, and we always have the equal number of predictions. So in case of MOTR, that's going to be 300. So we need some sort of way to match those predictions with the ground truth. So in good case, like this one, we actually have two predictions which seem to match the ground truth objects. Obviously, especially in the beginning of the training, that's not going to be the case, and we're going to have phantom predictions somewhere in the background. We might have more than one prediction covering the same object. We might have ground truth objects that are not actually covered by any predictions. And so what we need to do is we need to define how a certain prediction matches to the ground truth. So if I have this bounding box prediction somewhere in the middle, how do I decide where to match it? Like, is it matching to this bird or this bird? So this is where Hungarian matching comes along. So this is the problem statement for Hungarian matching. So let's say we have a certain number of model predictions, and then a certain number of ground truth objects, and infinite number of these implicit no object classes. So how do we connect them to each other such that some sort of loss over all these objects is minimized? And this is done by Hungarian matching loss. And basically what it does is it computes all possible permutations of model predictions, calculates the loss, and then chooses the one permutation that leads to the overall minimal loss. The actual Hungarian algorithm does not perform this brute force search over all permutations. It's much more effective than that, but it doesn't really change what is happening here. So I think it's easier to understand as just a full search over all possible permutations. And so in this easy case where the model predicted two birds and there are two birds in the ground truth, everything is more or less straightforward. So they got matched somehow, and then everything else got matched to no object. Here's a more complicated case where there's now three predictions for the bird and one prediction of a cat. And so Hungarian matching algorithm will do something like this, where two closest predictions of the birds will be matched together, and then one of the birds will have to be matched to this special no object class, as well as the cat. So this means that this Hungarian matching loss basically penalizes the model for phantom objects in the background. It penalizes the model for duplicate predictions as well as lack of predictions. So if, for example, we only had one predicted bird, then another bird in the ground truth now had to be connected to the object class, which is really what we want from the object detector. We want it to detect exactly the same object as there are on the picture, no more, no less. And so going over everything that's going on in DETR one more time, the input during training is going to be just an image, raw pixels, red, green, blue, and then ground truth objects, the actual bounding boxes, and classes. And class in this case is just a number from 0 to 80 corresponding to one of the Coco datasets classes. And the output of DETR is going to be a fixed set of predictions. In the original DETR that was 100. In MOTR that's going to be 300. And then for every prediction there's going to be a class probability or no object and predicted bounding box. So this means that instead of 80 predictions for classes, we actually have 81 with one extra prediction corresponding to this probability of no object class. And then the actual loss, we'll look at how good are we in drawing this bounding box. And for that, we use mean squared error, which basically tells us how far the actual pixels are. Second loss with that is IOU, intersection over union, which instead of looking at this pixel distance is going to look at the area of intersection of predicted bounding box and ground truth bounding box divided by the union. And that seems to work better for really small objects when the pixel distances are not that great, but still it's important to localize them correctly. And the second component in the loss is classification, which is just typical binary cross-entropy loss. Next, we want to take this DETR model and use it for object tracking. That is, to not only just detect the objects in one frame, but also generate some sort of consistent track ID that will match from frame to frame in a video. And basically how we're going to do that is we're going to take these object queries and make them carry over from frame to frame for the object that we did detect. And so in MOTR, it actually works exactly the same way as in TrackFormer, except that it's called slightly differently. So let's look at this example where we have a video and basically frame 1, frame 2, frame 3, and so on. And so we have one object that consistently is present in all the frames, another object that is only present in the first 3, and then another object present in the last 3. So what will happen is we will start with basically DETR, where we basically feed in new sets of these static, what they call detect queries, which are exactly the same as in DETR. And then we'll see that 2 of them actually matched ground truth objects, and we will promote them to track queries, and they will carry over to the next frame. So when we do detections for the next frame, what will happen is we'll feed in these 2 track queries that got carried over, as well as the new set of 300 detect queries, which are statically initialized. And so the output of decoder, which is exactly the same shape as input, will also have this extra 2 predictions for these 2 queries. And we will just say that whichever prediction we got out corresponding to this input query is going to be the corresponding detection of the same object in the next frame. And so in this case, we can see that we still have these detections from the previous frame. And then we detect one more object, which is also getting promoted to this track query. That again gets carried over, at which point we can see that this blue one now disappears. So it is fed into the decoder, but then decoder sees that it's no longer in the picture, and so it will not output that as an object. So this is, again, an example how that might look like. In frame 0, we have 300 object queries that are statically initialized, which means they are not actually dependent on the image, but they are trainable. Then after inference on the first frame, we detect 2 objects. So those 2 predictions, 2 output embeddings become track queries, and then they carry over to the next frame. And when doing predictions for the next frame, we'll still have the 300 statically initialized queries as well. So for the next frame, we actually will have 302 input queries and 302 predictions. Then when we perform inference for the second frame, we still get these 2 initial objects that carried over from the first frame, and then we detect another object. So this is now the 3rd detected object. So we now get 3 track queries that carry over. And then in the next frame, maybe 1 ground truth object disappears, 2 objects remain, and so on and so forth. So now going over what is happening in MOTR, the training input is now a sequence of up to 5 images, and this 5 here is a huge difference to TrackFormer. So TrackFormer only train on the actual pairs. Here we are actually training on the entire sequence. And then an object annotations, where every annotation has a consistent track ID for every image. So we're not just looking at detections, we also know the ground truth association of that detection from frame to frame. And that every annotation, again, has a bounding box, class, and track ID. And so the output of MOTR is, again, a fixed set of predictions. Well, actually not that fixed. It might be 300 or more, depending on the number of objects we already track. And then for every prediction, we also have class probability, predicted bounding box, but also sort of like a track ID, which is not really predicted by a neural network. So there is no had in the model that will just predict track ID number 3, for example. Instead, these track IDs are sort of implicit in the position of the query input and the embedding output corresponding to that, which we can turn into a track ID. Next, we need some sort of loss that will allow us to actually train the model in such a way as to preserve this track identity. And in data-like models, we can consider loss as sort of consisting of 2 steps. And so the first step is matching, when we decide which model output corresponds to which ground truth object. And the second part is the actual loss calculation. And so during matching, what we will do is we will look at track queries and just directly match them to the respective object, because we already know to which object that track query is supposed to correspond. And for new queries that we've just detected, so new detections in this frame, we perform the same old Hungarian matching to decide where to connect them to. And sometimes we'll have track queries for disappearing object, and those we just match to no object class. So this is an example of how that might look like. So let's say that there is a frame and there are 3 people that were on the previous frame, and then 4th person that just appears there. And so we will again apply the model. In this case, we would have 3 track queries inputs that sort of get carried over from the previous frame, and then typical 300 statically initialized detect queries, one of which will detect this person. And so the way it will look like from the matching perspective is that for these 3 queries, these 3 people, we don't have any special matching. We just match 1-to-1, explicitly knowing which query corresponds to which object. And then for the remaining things, we will perform Hungarian matching. In this case, the only actual ground truth object participating in that will be this 4th person, and everything else, and it will get matched to one of the queries, and everything else will have to be matched to an object. And so we can also think about that as a sort of extension to direct set prediction. So set prediction can be viewed as like, the word set here means that it's unordered. And so if you just have Hungarian matching loss, you would not care about order of model output at all. In the case when we actually need to preserve some sort of track identity, we can achieve that by taking out these queries out of this Hungarian matching loss, thus adding this order preservation part to the model as well. And then once the actual matching is done, so when we basically have the model outputs, first 3 of them were from the previous frame, detections from the previous frame track queries, and then the other 300 are new ones. And so they got matched somehow like this. And then one of these got matched here, everything else got matched to an object. So now when we have this matching, we can compute the actual loss, and the actual loss will be exactly the same as in DETR. So you will have some loss for bounding boxes, mean squared error, intersection over union. We'll have some loss for classification, cross entropy loss, and note that there is no explicit loss for track ID. So track ID is sort of implicit here. It's implicit in the order of the queries. It's implicit in the matching that we've done, but there is no actual loss component for that. Okay, next let's discuss training datasets and what sort of input the network actually gets during training. So the main challenge that people try to solve when writing papers about multiple object tracking is MOTA challenge. This is probably the most famous right now in the literature. It consists of video streams. Actually, let me just show you. So this is the website, the official website for MOTA challenge. Usually people just care about MOTA 17 version. You can see some video clips here. One thing to note instantly is that there's like a dozen of them. So the entire branch of science of multiple object tracking sort of focuses on these 30-second video clips for benchmarking all the current object detectors, which is which is too small. I guess like we don't have giant data sets for multiple object tracking, but that is how they look like. So in this one, we are only focused on people. We have 30 seconds of videos. That's something like 1,000 frames, and then we need to consistently track these people from frame to frame. The second sort of training data that we can use is just object detection datasets like CrowdHuman. So this is how CrowdHuman looks like. It's a bit like Coco dataset, but as you can guess from the name, it's more focused on the actual people, as the Mod 17 does as well. So we have static images, no videos, so no frame-to-frame tracking information, just static images with the actual bounding box annotations. So when training on a video stream, what we'll do is we'll sample some frames from the consecutive video, and we'll also apply what's called temporal augmentation. So instead of like first frame, second frame, third frame, and so on and so forth, we'll actually skip some frames randomly, like taking every fifth frame, for example. And that's basically an augmentation technique that allows us to take into account various frame rates, various cameras, and so on and so forth, so that if we're training on really high quality video and then we're going to apply our detector to low frame rate cameras, for example, it will still work well enough. And then we'll take 5 of these frames and basically feed that in to the model as a single example, as a sequence. And so we'll have the actual 5 images, 5 consecutive frames from the same video, knowing the ground truth, knowing the track IDs of objects that appear in all 5 of them. And during the actual training, we start with just the 2 images per sequence and then gradually increase up to 5 for the latest epochs in the training. And this longest sequence is the main difference to TrackFormer. And I think it's actually quite important for identity tracking. So if we think about an example like this, where the ground truth object, we have 2 people basically that basically move closer to each other and then again move further apart, right? So TrackFormer always trains on just pairs of images. So it will look at this image, for example, and then this image, and try to make connection like where the object from the previous frame is on the current frame, right? And as you might guess, the cases where something is close together, this is the most confusing case for heuristic trackers for sure, for transformer-based trackers, I would guess as well. And then moments like these are the most dangerous for cases like identity switch, when you tracked one object, then it got too close together with some other object, and now you're tracking that one instead. But if you just look at a pair of images, right? So if you look at this image and this image, the actual loss that you will get from incorrectly assigning these track IDs, incorrectly detecting an object, is quite small, right? So if you just confuse these 2 people, right, the loss that you'd have, the mean squared error and intersection over union, is also really small because, well, these 2 people are really close together. So the absolute difference in the correctness of detection is quite small. And so for this most dangerous case of objects being really close together, you would also get the smallest loss overall. And so you don't really train that effectively on them. This is fixed if you just take a longer sequence. So if you just take all these frames as a single sequence, and so the network confused these people, and so you don't have that big loss here, but then once the object actually started moving apart, you would see that the loss is now quite big because the objects are further apart. And so having these longer sequences allows you to train more effectively. This is example of how we can train on just static images. So this is an image from CrowdHuman dataset. And what we do to sort of turn it into a short video clip is we just apply image augmentation called random shift. So we just sort of shift an image back and forth a little bit, thus making sure that the actual pixels look differently in the different image. So you can see here that some details got shifted away, but then obviously pose and the actual look of the picture is still the same. So the quality of this one is not as good as the actual video clips, but as usual, object detection data, just static images, are more readily available. So we have a lot of these data sets, and it's much easier to collect your own object detection data set than object tracking data set, because annotating a single image is much easier than annotating every frame in the video. And so we do that because the data is easier to get. We take an image, and then that's our one frame, and then we apply random shift to that image once or several times to get consecutive frames. Now let's talk about time aggregation network. So time aggregation network, or TAN or KEM as it's sometimes called in the paper, is basically an extra transformer layer that controls how queries are passed around from frame to frame. So we can see that on an example. So here we have a video stream. We have frame 1, frame 2, frame n. So each frame is being fed into the model independently. So we have this frame, it passes through encoder, through decoder. So the first frame will only have these statically initialized detect queries. It will go through the decoder, and then it will output some sort of embeddings. And so these embeddings will be used to generate the actual prediction for this frame, but then they will also be passed through this extra layer to become the track queries for the next frame. So this transformer layer is just a normal transformer, full self-attention. It only operates on those queries that actually matched with some ground truth objects. So that's the main difference to layers in the decoder, for example, because in the decoder, you'd always have 300 plus queries coming in as an input, whereas for this extra layer here, you would only have like 3 queries. And that's basically an extra step that allows the model to look at only the detected objects one more time and basically have some differentiation between the actual output and this carrying over of queries from frame to frame. Other than that, that's pretty much the same as it was in TrackFormer. So in TrackFormer, instead of being passed through this network, we just copied those queries directly to the next frame. And here we just deploy an extra self-attention transformer layer. And so once again, main thing why that's needed. First of all, this extra layer only looks at the actual queries that track some objects, which is the number of those are usually much smaller than the total number of queries. So total number of queries is usually 300. And then for tracking queries, you'd have 0, 1, maybe 15, but not that much. And it also allows the network to store some different sort of information for the cases where it needs to pass it to the next frame, as opposed to just do the prediction for the current frame. Now let's go over main differences and similarities to TrackFormer between MOTR and TrackFormer. So first difference is that we actually train on up to 5 frames per second instead of just a single image and sort of aggregating information from the previous image as well. And this is also referred to as collective average loss in paper. But really all that is that we take 5 images and then average the loss across all of them. But it's really important because it actually allows the network to be penalized for this long-range identity tracking errors and complicated cases when objects move closer together and then drift apart and so on and so forth. So this thing is really helping for the actual identity tracking. The second difference is that there's an extra attention layer called time aggregation network, TAN, for this process of carrying over queries from model output from the previous frame to the next frame. And in TrackFormer, that was plain copy. And then ablation studies of MOTR show that that actually is supposed to help, although, as we'll see in the results section, I have doubts about that. Another small difference is that during inference, during actual evaluation, when we don't know ground truth objects, MOTR does not use non-Maxwell suppression, which is quite good. You want something that works without heuristics, and NMS can be quite slow, although due to the transformers used in the model that are not like RT-DETR, for example, the transformers themselves will be very slow, so MOTR as TrackFormer as well is not going to work that well for resource-constrained systems like robots, for example. There is also no special heuristics for re-identification, partly because we have this long-range identity tracking on its own, so we might not need that explicitly. The model should be able to handle that, although it's hard to say like how well that actually will work. And the rest is pretty much the same. So although the naming used is different, so TrackFormer just uses queries, and then MOTR uses tracking queries and detection queries, the actual concepts are all the same. And the authors of MOTR actually say that they sort of started the work independently of TrackFormer, and then the TrackFormer published results slightly earlier, but they didn't try to steal from them. Despite that, the actual models came out quite similar in their overall look. Now let's talk about the results. And it's quite a complicated topic because of, I'd say, the mess with metrics that sort of was going on in the recent history. And so to actually understand like what is better, MOTR or TrackFormer, and what is the current state of the art, we need to understand what sort of metrics we have, and then discuss the results. And so the most famous metric for multiple object tracking used to be MOTA, because of MOT challenge, because it was the official metric to actually compute the leaderboard for object trackers. And we'll see that this metric actually has some problems, which is quite unfortunate because it was the most widely used in the literature. And the way this metric is calculated is basically the following. So we start with just detection quality, and to assess detection quality, we have our ground truth objects, this person, for example. We have detections, like this red bounding box, for example. And then we'll only count it as a match if intersection or union is above 0.5. Then we will obviously have cases when some objects are not really covered by anything, or there are multiple predictions covering the same object, or it's really not clear which object this prediction is covering. And so to handle these cases, we'll also use Hungarian matching. Yes, the same Hungarian matching that is used in DETR is used in the metric as well, which is a bit strange, but this is the only way it could work. And so we'll perform Hungarian matching to optimize this overall average similarity between predicted bounding boxes and ground truth objects, thus creating this connection, like which object is covered by which prediction. And so in this case, some objects will be correctly covered by a bounding box, and that yields a true positive. But then some objects will not be covered by predictions because the detector failed to detect them, for example, and that's a false positive. And then again, some objects might be covered by more than one prediction, or some predictions might not really correspond to anything, some phantom stuff in the background. All of those are counted as false negatives. And as you might notice, these metrics are only looking at one static picture. So it's basically the same as detection. To actually turn that into a metric for assessing object trackers, we have a final component called identity switch. So an identity switch now looks at the actual trajectory, the actual sequence of frames in a video, and it just tracks the cases when the same ground truth object was assigned one track ID by the tracker and then got switched to another track ID. And by switching, we mean that for the next frame, this Hungarian matching laws that still looks at this IU threshold of 0.5, assigned it to a different object. Now, the problem with that is really well articulated in the paper for this new HOTA metric. And we can basically describe it as the following. So imagine we have some sort of object, and you can imagine that it's a criminal who stole something and is trying to get away from the police. And so the ground truth object sort of exists all throughout our video sequence in hundreds of frames. And so detector A correctly identifies this criminal, but only half of the time, so 50% of frames, which gives the police plenty of time to actually catch him, right? But then for the remainder of the video, we are not really detecting anything. And now detector B is slightly better at detection, so it's actually detecting something 70% of the time, and only 30% of the time it's not detecting anything. But then only for 35% of the time it's detecting the same person, the criminal. And then the second part of the trajectory here is basically reinitialized with a different track ID, at which point we can no longer say that this person is indeed the criminal that we are chasing, and basically we've lost the criminal at this point. So this trajectory actually gives the police only 35% of the time to catch him. So the first one is actually better for criminal catching case. And then extreme example of C, again, 4 independent detections, 4 independent track IDs, but now the detections cover 100% of the time. And so if we look at the detection accuracy, which is MOTA without that identity switch component, we'll see that it just basically looks at correctness of detections. For that, we don't really need object tracking. We can go with just an object detector like YOLO or DETR or something like that. And so for the first detector, it will be 50%, then 70%, and 100%. So it's only looking at detections for individual images. And the actual MOTA metric that now uses this identity switch is actually almost the same. So in the first case, there is no identity switch, so MOTA is 50%. In the second case, there's just one identity switch. There it is. But it's only contributing to like 1% of the metric. So it's not really doing that much. And then in the last case, we have 3 identity switches. So the metric got this small penalty. But again, it's not that much. So from MOTA perspective, not caring about the actual identity and just focusing on detection is the winning strategy. And the authors of this HOTA paper actually analyzed leaderboards, analyzed competition results, and did indeed prove that this identity switch thing only contributes to about 1% of the overall score, which is really not enough, because the main thing we care about is to actually track objects consistently from frame to frame, and it's not really that good to have that so underrepresented in the metric. And so to compensate for that, what we used to look at were these 2 metrics, assignment accuracy and IDF1. Oh yeah, and I forgot to show this. This is the actual definition of MOTA metric. So it's 1 minus sum over all the time frames of false negatives, false positives, plus identity switches, divided by the number of ground truth objects. And you can see from this definition why identity switches are so undervalued, because you'd have a bunch of false positives and false negatives on every frame, whereas identity switches are quite rare, so their overall contribution will be quite small, although obviously it's enough to lose the criminal just once, to lose him forever. So we definitely need something better here. So historically, to measure this identity tracking of our object trackers, we would look at metrics like IDF1 or assignment accuracy. And basically what it does is it now looks at the entire trajectories. So it will look at ground truth trajectories from the provided track IDs. It will look at predicted trajectories of the predicted track IDs. And then we will have the same problems as with detection, where some trajectories might not be covered by anything, some trajectories might be covered by more than one prediction. And so to decide how to match one to the other, we're also going to perform this Hungarian matching. But now we'll look at the entire trajectory. And as actual metric, we'll use either the accuracy, which is just the actual intersection between the true trajectory and the predicted one that got matched, or the slight rebalance of this one called IDF1, which is basically measured a little bit differently to give more weight to recall as opposed to just precision. And so for our criminal case here, we'll see that the first case is actually the best for assignment accuracy. So it has 50%, and then it drops to 35%, roughly corresponding to the amount of time the police would have to actually catch this criminal. And then IDF1 does look the same directionally, but the actual numbers are slightly different. And so HOTA metric, which was proposed quite recently, so it's 2020, unfortunately, because it's still not used in all of the papers you see nowadays, TrackFormer included. So HOTA metric actually tries to balance these two. It's basically a geometric mean of detection accuracy and assignment accuracy. And in this case, it actually measures all of these trajectories as equally good. And here are the results of MOTR on this MOT17 challenge. So here they basically have two sets of comparisons, one to the old style heuristics, and we can see that current state-of-the-art buy track is ahead of pretty much everyone else, whatever way you look at them. So HOTA, IDF1, MOTA metric, all of them are better for this buy track than for MOTR. They also compare their model to other transformers like TrackFormer, although here I do believe that they misquoted the actual results from the paper. So the correct ones should be roughly 68 for IDF1 and 74 for MOTA. So if we actually look at TrackFormer paper, they have two sets of results, the MOT17 private, MOT17 public. So public leaderboard is something really weird because they basically rely on existing detections from some object detection model, and then they compare heuristic-based object trackers using these common existing detections. That's not really applicable for end-to-end object detector like TrackFormer or MOTR, so you shouldn't even look at this part of the page. Don't. What you should look at is these private detections, which are basically just evaluations of this model in an end-to-end settings. And you can see here that MOTA metric is 74, IDF1 is 68, which, coming back to our MOTR results, are pretty much the same for MOTR. So it's 67.6 for IDF1, 73.4 for MOTA. So the numbers look similar, so I can't really say based on these results that MOTR is better than TrackFormer. TrackFormer seems to be exactly the same. In either case, both of these are inferior to old-style heuristic, state-of-the-art like bike track. MOTR authors also evaluated the model on some other datasets. So on one of them called dance track, so this is how dance track looks like. Pretty much, as you'd guess, the object tracking of people dancing, which might be more challenging for heuristic-based object trackers because of variety of motion and poses and all of that is happening here. And so this is exactly what we see on the leaderboard. Here, MOTR actually managed to outperform and become the state-of-the-art, although I don't believe that TrackFormer actually tried to evaluate on this one. Maybe it would beat them as well. And also, this, depending on what you are interested in, MOT17 sounds like a more close to real-life, realistic example of what tracking is, and not dance track. Another one, BDD 100K. So again, this one is for autonomous driving, and it basically consists of footage from a driving car, and we have annotated objects for cars, pedestrians, cyclists, and so on and so forth. Again, here MOTR authors choose to compare to some weird models. DWI, what is that? I don't really know. But there are existing relations of the same state-of-the-art by track, for example, and it is better than MOTR. So it's a bit weird that they chose not to put that into the actual result table. So to sum up, results on the main dataset MOD17 seem to be similar to TrackFormer, which is really weird because if you look at the ablation studies in the MOTR paper, they will tell you stuff like the metric improved by 8% from this collective average loss and using 5 frames, and then it improves by something like 6% from this time aggregation network, and so on and so forth, despite the fact that TrackFormer uses none of these and still get the same result. So it's really weird, to say the least, to have the authors say that. Nevertheless, deep learning world is quite complicated. We know that just slightly different code, slightly different training parameters might lead to drastically different results. So to get more precise results, you actually need a lot of experiments. So I'm guessing that might get solved in the future. Once again, MOTR, as TrackFormer as well, is not state-of-the-art. It loses to other heuristic-based detectors, trackers like ByTrack on pretty much everything. And the only example I could find, and the authors could find where it's not the case, is DanceTrack, which is fine, I guess, but then not everyone actually evaluates on DanceTrack, and the dataset itself is not that representative of how we typically use object trackers. And then one potential problem that we know about, like why are these models like MOTR and TrackFormer are actually inferior to heuristics, is that the actual DETR and deformable DETR object detectors used as a core component of the model are also themselves inferior. So we have a bunch of more modern object detectors that are based on the same architecture, like Dino and CoDETR, that really took it to the next level. So maybe using them as a core component of object tracker might improve the state of things, although it has its challenges as well. MOTR v2 actually does something like that. So it's actually using YOLO as the sort of second auxiliary object detector, and it actually achieves quite promising results on object tracking benchmarks. So that's it for today. Thanks everyone for listening, and hope to see you soon.